Welcome back, Pre-Calc Excel students. We're going to finish the notes for 10.6 today, and we're going to start off with example 4. So we're asked to sketch a curve represented by these equations by eliminating the parameter. So just like the last example, we want to first solve for cosine theta and sine theta. Okay, so I'm going to divide by the 3. In this equation, I'm going to divide by the 4. And then we're going to use the Pythagorean identity. So x over 3 squared plus y over 4 squared will equal 1. So I end up with x squared over 9 plus y squared over 16 is equal to 1. So we skipped over the beginning of this chapter, which covered the conic sections, but do you remember from Algebra 2 what kind of conic section this is? When you have a sum and these values are different, this is going to be an ellipse. So we can use our chart to plug in some values and get the orientation and get some points on the graph. So if we start with the minimum value of theta, which is 0 degrees, we'll go in degrees. Let's see, then the cosine of 0 is 1, so x is 3, the sine of 0 is 0, so y is 0. At 90 degrees, the cosine is 0, and the sine is 1, so y is 4. At 180 degrees, the cosine is -1, so this is -3, and y is 0. And at 270 degrees, x is 0, y is -4. So we can plot these points. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. So if I sketch my ellipse, it's going to look something like this. And then the last thing I'm going to do is include that orientation. So remember, the orientation is determined by the order in which you plot your points by increasing values of theta. So if we start at 3, 0, the next point we plotted was 0, 4, then -3, 0, then 0, -4. So this graph has counterclockwise orientation. So we just throw a few arrows onto there to show the orientation of the curve. And that completes the sketch. Okay, the next example. Now, in this example, you're going to find the parametric equations. Okay, given y is equal to 4x minus 3, and then there's infinitely many possibilities. So to narrow it down a little bit, you'll be told what t equals. So in this case, t is equal to x, so that means x is equal to t. And then to get the y equals equation, I replace the x in the original rectangular equation with what x equals. And in this case, x equals t, so it becomes 4t minus 3. For this one, t is equal to 2 minus x. I'm going to solve for x. So I'd add x to the side, subtract the t. And now for the y equals equation, I'm going to go back to the rectangular and replace what x equals in this equation. So I end up with 8 minus 4t minus 3, which is 5 minus 4t. So my second equation is 5 minus 4t. Okay, so that takes care of that type of example. Let's move on to, oh, I have an extra example. So this one, a little more complicated, but this would be a good time to pause the video. Try this one on your own. Solve for t just like we did. Plug that into the second equation and see if you can come up with the rectangular equation. So this isn't like the last example. This is like one that we've done previously on the last set of notes, where you're coming up with the rectangular equation by eliminating t. So go ahead and give it a try. When you're done, you can come back and I'll show you the solution. Okay, so let's see how you did. Okay, so hopefully you ended up with the rectangular equation 1 minus x squared. Okay, so it'll be y equals 1 minus x squared. Now I put a comma here because this is actually not complete yet. Did you remember that you need to think about the restrictions? In this case, t has to be greater than -1, right, to ensure that this is greater than 0. So what comes out of this expression will always be greater than 0. So the restriction on this graph is that x must be greater than 0. So we end up with just the one part of the parabola, right, where x is greater than 0. Okay, the last part of this section, we're going to go over projectile motion. So there's a pretty interesting little blurb here about pumpkin tossing. It fascinates me that this pumpkin went almost a mile, which, you know, poses a couple of questions. Number one, how did they track that pumpkin back in 1998 to know how far it went? And secondly, I hope nobody was injured in the process, because that's a pretty far throw. So anyway, on to our parametric equations that can model nonlinear motion. So consider an object that's projected into the air at an angle theta with an initial speed of v. The object's parabolic path can be modeled with these parametric equations. So there's the v, okay, which is that initial speed, and theta, which is again the angle in which it's projected. So in these equations, x sub 0 and y sub 0 is the object's location when the time is equal to 0. The constant g is the acceleration due to gravity, which is either 32 feet per second squared or 9.8 meters per second squared. So we have a pumpkin tossing contest where, let's see, a contestant won the catapult competition by using 2 telephone poles, huge rubber bands, and a power winch. So suppose the pumpkin was launched with an initial speed of 125 feet per second at an angle of 45 degrees and from an initial height of 25 feet. Now keep in mind your units are important. I'm going to give you a little hint. There's a baseball problem that you have to do for homework, where the pitcher's throw, I believe, is given in miles per hour. You have to make sure that your units are in feet. Okay, that again goes back to here, where this is 32 feet per second, 98 meters per second. So if you're using feet, that's, you know, and you're given miles per hour, you need to do that conversion. That's always a reason why some people get that baseball problem wrong, because they don't convert. Okay, so back to this one, we don't have to worry about any conversions here. You're asked to write a set of parametric equations for the motion of the pumpkin, and then use the equations to find how far that pumpkin traveled. So go back to this page, use these parametric equations, plug in what you know, set up the parametric equations, and then see if you can calculate how far that pumpkin traveled. So pause the video, give it a try, and then when you're done, come back and we'll compare solutions. Okay, for the equations. So we're using that 125 feet per second, 45 degrees for theta, and x sub 0, y sub 0 is 0.25 because it's starting at that initial height of 25 feet. So hopefully you came up with this equation for x and this equation for y. For part 2, the pumpkin hits the ground when y is 0. Right? Y are all of those heights over the time. So solving for the time, you'd get 5.8 seconds. When the time is 5.8 seconds, the pumpkin's location will have this x value, so it traveled about 513 feet. So that concludes the 10-6 lesson. I hope you enjoyed it. It's interesting stuff. I think it's new to all of you, so hopefully this sparks some sort of interest in parametric equations. We'll be moving on to section 10.7 and 10.8, and your next quiz will follow those sections. So if you have any questions, remember you can meet me on Zoom any day from 11 to noon. The link and password are on the website. So have a good day, and I hope to see you soon.